So may I present now Murry, all the way from Australia. Thank you for coming.
Thank you, Philip, and thanks to the Climate Committee for hosting this visit. It's good to be here. Or in the immortal words of Keith Richards, it's good to be anywhere. I bear tidings from the Flat Earth Society. If a prerequisite for membership is critical thinking, sign me up. Critical thinking is what distinguishes us from our ancestors, who were guided not by reason, but by irrational fervor. It's behind the great advances in the human experience. Critical thinking is what brought us out of the Dark Ages into the Age of Enlightenment. Its importance to who we are is expressed nowhere more succinctly than it was then. I think, therefore I am. And if there's one place where critical thinking should prevail, it's the university. Critical thinking is hardly cause for embarrassment. If anything is worthy of scorn, it is the marginalization of critical thinking. At its core is questioning, embodied in the Socratic method, teaching. It's the guiding light through which we have advanced. We learn by questioning. That time-tested principle is intrinsic to institutions that make our civilization modern. The law, governance, and nowhere more central than science. And so, when I found myself writing a new book on the atmosphere and climate, and seeking what was and was not understood, I was compelled to do as I have for 40 years of research, to question. The question most fundamental was on the relationship between greenhouse gases and global temperature. Recent attention is focused on the conspicuous discrepancy between the evolution of global temperature that was predicted by climate models versus the evolution that actually occurred. The predicted evolution rests on the interpretation of warming during the 80s and 90s, when temperature and CO2 both increased. The IPCC held that global temperature increased then because CO2 increased. After the 90s, temperature should have continued to increase, as in the consensus of climate models. The mean of the spaghetti. It didn't, even though CO2 did continue to increase. In some data, temperature steadily decreased. The interpretation of warming in the 80s and 90s has been contradicted by subsequent changes. The absence of warming after the 90s has continued for nearly 2 decades, almost as long as the presence of warming during the 80s and 90s. That's a long time in the career of a scientist or a bureaucrat. But relative to variations of the Earth-atmosphere system, it's the blink of an eye. The picture wasn't as simple as they thought. The interpretation of warming in the 80s and 90s, on which climate predictions rest, has been invalidated. For many, that's enough to go home and get a good night's sleep. But if you think the issue has evaporated, you're deluding yourself. Consecutive years of warming during the 80s and 90s was an infrequent event. But like Category 5 hurricanes, it was inevitable. Likewise for consecutive years of cooling, which also punctuate the observed record. A decade or two of warming happened earlier, during the 20s and 30s, it will happen again. And when it does, CO2 will still be increasing. No, there's only one way to truly resolve this issue. Understand why greenhouse gases like CO2 change. Central to interpretations of climate change, that was the conspicuous question that surfaced when, to produce a new book, I sought a broad understanding of the subject. I wanted to understand how much of the increase in CO2 follows from physical influences, factors unrelated to human emissions. As you're about to see, this issue is pivotal. The IPCC's position is the natural contribution to increased CO2 is zero. For the industrial era, Earth was therefore a very dull place. CO2 and anything it influences were constant. Then, during the 19th century, someone switched on the lights. I've worked with atmospheric data for 40 years. I've yet to find anything that is constant, especially trace species like water, ozone, and CO2. I work with data, not because it's my principal focus. It's not. Most in the field would say I'm a theoretician. I stay close to data to keep me honest. Otherwise, it's easy to lapse into a self-fulfilling prophecy, a theoretical universe where one becomes proof for another. The IPCC's position on CO2 is exclusive. There's a reason. If as little as 10% of the observed increase follows from natural emissions, attempts to control atmospheric CO2 by limiting human emissions of CO2 would be pointless. Even driving human emission to zero, which would require the elimination of humans, would merely postpone the inevitable. Albeit more slowly, CO2 would then continue to increase from natural emissions, over which we have no control. CO2, methane, and other greenhouse gases contribute to atmospheric composition. Except for water vapor, however, even collectively, they represent less than 1% of the atmosphere. In fact, far less than 1%. The explanation advocated for changes of atmospheric composition, along with their implications for temperature, rests on three pillars. 1. Proxy evidence of the past atmospheric composition. 2. Modern changes, those actually observed. And 3. Simulations of their impact on climate models. For past changes, observations do not exist. We have only proxy evidence from ice cores. The proxy record relies on air bubbles that become embedded in glacial ice as it sinks in the weight of the overlying column. In green is the record of proxy CO2. It changes by 100 parts per million by volume, ppmv, on the timescale of 100,000 years, with smaller changes on shorter timescales. In mauve is the record of proxy methane. It too changes, mirroring changes of CO2. In blue is proxy temperature, inferred from isotopic oxygen. It changes in similar fashion, undergoing swings of 8 centigrade in the Earth's glaciation cycle. Temperature, that's anomalously cold, coincides with ice ages, accompanied by CO2 and methane that are anomalously low. Temperature that's anomalously warm is accompanied by just the reverse. These ancient changes of composition are the linchpin of modern interpretations. They are the reference against which changes during the 20th century, those actually observed, appear unprecedented. Plotted here is the cross-correlation between proxy temperature and CO2 as a function of the lag gap between those records. It measures the interdependence of temperature and CO2. Their cross-correlation exceeds 0.8. Changes of temperature and CO2 are strongly interdependent. If one changes, so must the other. Nearly symmetric, the cross-correlation decreases with lag, slower for positive lag, where changes of CO2 follow changes of temperature. First temperature increases, then CO2 increases. In fact, their correlation maximizes at small positive lag, less than 1,000 years. These changes refer to proxy CO2 in ice, not atmospheric CO2 actually observed. We need to understand how the two are related. This is the observed record in actual measurements of atmospheric CO2 and temperature. It extends back half a century. CO2 increased steadily during the 20th century by about 30%, 100 ppmv. Global temperature did not. It fluctuated, warming during some periods like the 80s and 90s, but cooler during others. Plotted here is the cross-correlation between observed CO2 and temperature. It exceeds 0.5 at positive lags. Changes of CO2 follow changes of temperature. As in the proxy record, observed CO2 and temperature are also strongly interdependent. Their correlation maximizes near a lag of 10 months. An increase of temperature is followed 10 months later by an increase of CO2. The delay tells us something about cause and effect. Although maximum near 10 months, the correlation between CO2 and temperature is significant across a wide range of positive lag. The asymmetry indicates that observed CO2 evolves dependently with temperature across a wide range of time scales. And on all of them, changes of CO2 follow changes of temperature. CO2 is produced and destroyed at the Earth's surface, but in the atmosphere, it's conserved. Its rate of increase, the growth rate of atmospheric CO2, must therefore equal net emission from the Earth's surface. In green is net emission of CO2, collectively from all sources and sinks, human as well as native sources. Unlike human emissions, native sources and sinks are sensitive to surface conditions. Field measurements, those where CO2 emissions was actually observed, revealed that native emissions depend strongly on temperature. In blue is global surface temperature. Net CO2 emissions tracks the history of surface temperature, achieving a correlation of 0.63. During the satellite, when we have global observations, it achieves a correlation of 0.8. Notice the correspondence holds even for systematic changes during the last half century, when net emission intensified by 100%, from 1 ppmv per year to 2 ppmv per year. The observed relationship means that to leading order, net emission of CO2 is proportional to temperature. Now, CO2 during a particular year is just the sum of net emissions during preceding years. Net CO2 introduced in one year, plus net CO2 introduced in the next year, and so forth. As the net emitted each year is proportional to temperature, CO2 must therefore evolve the sum of annual temperatures. For those who remember their calculus, like the time interval of temperature. Each passing year sees the addition of another increment of CO2, which in turn is proportional to the temperature. In the observed record, CO2 thus also evolves dependent on the temperature. But there, it evolves not like temperature directly, as it does in the proxy record, but like the sum, or the integral of temperature. CO2 evolves dependently with temperature in both the proxy record and the observed record, but their relationship with those records differs fundamentally. To connect the two, we must consider the evolution of CO2 in ice. The evolution of CO2 is controlled by its budget, which accounts for its introduction and removal, first in the atmosphere and later in ice. They determine the growth rate of CO2 that's apparent in ice. The growth rate of CO2 must equal its rate of net emission from the Earth's surface, which you've seen intensifies with temperature, minus its rate of removal through dissipative processes. Removal of CO2 intensifies with its concentration. More CO2, faster it's removed. The budget of CO2 leads to a system of equations. Its solution determines the cross-correlation between CO2 and temperature. The diagnostic evaluated earlier from the proxy and observed records. The calculated evolution assumes two limiting forms. For timescales much longer than those in the observed record, the growth rate is slow. The budget of CO2 then reduces to a balance between temperature-reduced emission and CO2-dependent removal. CO2 growth rate is then limited because emission is offset by removal. In this limit, CO2 is removed by dissipative processes, almost as quickly as it was introduced by temperature-induced emission. Under this limiting balance, CO2 evolves directly with temperature. If temperature increases, CO2 increases. If temperature decreases, CO2 decreases. These conditions are manifest in the proxy record, which involves timescales longer than several thousand years. This is the calculated cross-correlation between CO2 and temperature in the limit of long time scale. Look familiar? At the bottom, the cross-correlation evaluated earlier from the proxy record. At the other extreme are timescales much shorter than those in the proxy record. Changes are then fast. The budget of CO2 then reduces to a balance between the growth rate of CO2 and temperature-induced emission, which is then uncompensated. CO2 growth rate is therefore unlimited. CO2 can grow arbitrarily fast, depending on temperature. In this limit, CO2 removal by dissipative process can't keep up with its introduction by temperature-induced emission. Under this limiting balance, CO2 again evolves with temperature, but now like the sum, or the integral of temperature. If temperature increases linearly, CO2 increases quadratically, even faster. If temperature levels off and becomes constant, CO2 increases linearly, slower, but it still increases. These features are manifest in the observed record, which involves timescales shorter than a century. This is the calculated cross-correlation in the limit of short time scale. At the bottom, the cross-correlation evaluated earlier, the observed record. If dissipative processes in ice are absent, the signature of atmospheric CO2, the embedded air bubbles, descends with ice conservatively. Under these circumstances, changes of CO2 imprinted at the top of the ice column are preserved. Changes of proxy CO2 then replicate changes of atmospheric CO2. If, however, dissipative processes in ice are represented, the signature of atmospheric changes is damped. How much it's damped depends on the timescale of changes. This feature of the calculated evolution is embodied in the power spectrum of CO2 in ice. The variance of proxy CO2 at one frequency or time scale versus at another. The power spectrum can also be calculated for zero dissipation in ice. What would have been registered in ice under conservative conditions. That, in turn, represents variance of CO2 in the atmosphere. The quotient of variance under these two circumstances describes frequency by frequency, that is, time scale by time scale, how changes of atmospheric CO2 relate to changes of proxy CO2. The quotient exceeds 1 for all time scales. Variance of atmospheric CO2 is thus larger than that apparent in proxy CO2. Equivalently, changes of atmospheric CO2 are underestimated in the proxy range. Their underestimation increases with time scale. At high frequency, short time scale, the quotient approaches 1. There, changes of atmospheric CO2 are nearly identical to those of proxy CO2. But at low frequency, long time scale, the quotient rapidly increases. There, changes of atmospheric CO2 are significantly underestimated by changes of proxy CO2. The effect is illustrated for conditions that recover the cross correlation in the proxy range, seen earlier. Change of proxy CO2 on a timescale of 100,000 years then underestimates the change of atmospheric CO2 by a factor of 15. Changes of proxy CO2 of 100 ppmv on the Earth's glaciation cycle then derive from changes of atmospheric CO2 of order 1,000 ppmv. Observed changes during the 20th century are then hardly unprecedented. This behavior has two key implications. First, dissipative processes inherent in the proxy range enable past atmospheric changes to be significantly underestimated. This is especially true of long time scales, those with the largest changes of past CO2, the ones against which modern changes are compared. For those changes, even weak dissipation leaves the respective change of atmospheric CO2 significantly underestimated. More importantly, the same physical mechanisms which describe ancient changes, timescales longer than several thousand years, also describe modern changes, timescales shorter than a century. And that brings us to modern changes, those actually observed. The observed record of CO2 spans the last half century. Extending it back with the proxy record indicates a systematic increase since the 19th century. In red is delta 13, the relative concentration of two isotopes, carbon 13 to carbon 12. It evidences a decline, mirroring the increase of CO2. Together, these proxy records comprise the smoking gun of human emissions. Vegetation is slightly leaner than carbon 13 than the atmosphere. So is its ancestor, fossil fuel. Coal and oil each derived from ancient vegetation. Combustion of fossil fuel therefore adds CO2 to the atmosphere, enriches its concentration. That's the green curve. The CO2 added, however, is leaner in carbon-13 than the atmosphere, thereby diluting its concentration. That's the red curve. The glove fits. In truth, however, it's but one fit. Combustion of fossil fuel is one of many sources of CO2. Others involve a wide range of native processes. Most are poorly documented. The recent interpretation is that opposite changes of CO2 and carbon-13, the green and the red curves, are the signature of human emissions. For this interpretation to be valid, other sources of CO2, native sources, must have the same concentration of carbon-13 as the atmosphere, which would then be left unchanged. That is, CO2 emitted by native sources must not dilute carbon-13 in the atmosphere. The observed increase of CO2 and decrease of carbon-13 can then follow only from the human source. In reality, our knowledge of native sources is limited. The little we do know is that native sources are dynamic. Native sources depend intrinsically on environmental conditions: cloud, moisture, temperature. Why should you care? This is the estimated contribution from all sources of space. The human source is of order 5 gigatons per year. By comparison, the ocean emits of order 90. Land emits another 60. Total emission from native sources is thus of order 150 gigatons per year. 96% of the total. It's approximately balanced by native sinks, which absorb about as much. The key word, approximately, because native sources and sinks are 2 orders of magnitude stronger. Even a minor imbalance can overshadow the human source. Moreover, if those sources involve carbon-13 leaner than in the atmosphere, as many do, all bets are off. In truth, only one component of the CO2 budget is known with any certainty: human emissions, implicit to records of extraction. How much coal and oil are dug up? It accounts for only 4% of the total. The other 96% from native sources remains obscure, because global observations of emissions do not exist. We have continuous records from only a handful of sites, and even those are records of CO2, not its emissions, which drives the atmospheric budget. This leaves the dominant sources of CO2, the big errors, not sharp, but fuzzy. If they change, we haven't the observations to know. At least not directly. Fortunately, that's not the end of the story. What controls atmospheric CO2 is net emissions, collected from all sources of source. Net emissions equals the rate of increase of global mean CO2, the average over the Earth. Because it's conserved in the atmosphere, CO2 is homogeneous by the circulation. This is the global distribution of CO2, only recently available from satellites like SAMAR. Even these modern observations are limited to continents, but that's where the human source is. Large values in yellow and red are a signature of source regions. Notice they're not found in the industrialized centers, the Ohio River Valley of the U.S., or Western Europe, or even China. Rather, they appear in the Amazon basin, tropical Africa, and Southeast Asia. Those regions have little human population, let alone industrialization. What I really want you to notice is that even in those source regions, CO2 deviates from its global mean by less than 5%. Local values are therefore a good approximation to global mean CO2, which through its rate of increase provides the history of net global emissions. In green is net emissions during the satellite, when we have global observations of temperature. It is an average of about 1.5 ppmv per year, but it varies between years dramatically, by over 100%, from nearly 0 in some years to almost 3 ppmv per year in others. Do I need to tell you that human emission doesn't do anything like this? In red, human emission increased smoothly. It mirrors the growth of human population, with deviations of only a couple of percent. By contrast, observed deviations of net emissions exceed 100%. They are incoherent with human emissions. Net global emissions evolves independently of the human contribution. The record of net emissions does, however, resemble surface problems. During 1991-92, net emissions decreased by 70%. It gradually rebounded over the following 3 years. That event coincided with the eruption of Pinatubo, which decreased global temperature in the same fashion. During 1997-98, net emission increased by 200%. That event coincided with the El Nino event, which increased global temperature. The correspondence during these events is consistent with field measurements of CO2 emissions. They reveal strong sensitivity to surface problems. Temperature seen earlier supported over time by soil moisture. An increase in either induces increased emission of CO2 from native sources. The contribution from induced emissions follows by projecting the observed record of net emission, that's the green curve, onto contemporaneous records of temperature and soil moisture. In blue is the induced component of net emission, the part that operates dependently with surface properties. Although it accounts for only 2 key properties, the induced component closely tracks net emissions. It achieves a correlation to the observed record of 0.93, accounting for nearly all of the history of net global emissions. Most of the dependence comes from temperature alone, which achieves a correlation of 0.8. In red is observed emission of carbon-13. It has a mean that's negative, consistent with the decline of carbon-13. But like CO2, it varies dramatically by more than 100%. In blue is minus the inducement, the part that operates dependently with surface properties. Like CO2, it varies coherently with observed emissions of carbon-13. Just opposite. When temperature increases, emission of carbon-13 decreases, and vice versa. Likewise, when CO2 net emission increases, that's the green curve, carbon-13 net emission decreases, that's the red curve. Does this ring a bell? Remember the smoking gun? Opposite changes of CO2 and carbon-13 are the same ones apparent in the icebox. The latter is regarded as a signature of human emissions, but in the satellite record, the changes are clearly not from human emissions. Not unless you believe human emissions caused volcanic eruptions in El Nino. In mauve is the observed record of methane emissions. It suffers from the same limitations as the record of CO2, but it's even shorter. It's noteworthy that human sources of methane are independent of human sources of CO2, unless you believe combustion stimulates bovine flatulence. In blue is the induced component, the part that operates dependent on temperature and soil moisture. Same surface properties, which account for most of the history of net CO2 emissions, also account for most of the history of net methane emissions, achieving a correlation of 0.94. That's what you saw in the proxy record. The first approximation, the blue curve for induced emission, is just temperature. It follows from the sensitivity of native emission, the part induced by changes in surface properties. Adding that emission over time, namely the induced CO2 introduced in 1 year, plus the induced CO2 introduced in the next year, and so forth, yields the cumulative CO2 introduced by the change in surface properties. That, in turn, is the contribution to observed CO2 from native sources, the ones that depend on surface properties. In blue is the induced component of CO2. It's determined entirely by surface properties, temperature from the satellite MSU, and soil moisture from meta-analyses. In green is the observed record. In blue is the induced component of methane. It too is determined entirely by temperature and soil moisture. Notice, after the early 90s, the trend in the induced component nearly vanishes. In mauve is the observed record. The sensitivity of native emissions, evaluated during the satellite era, should in principle determine the induced component in earlier years. But before the satellite era, global observations are lacking. Most of that sensitivity, however, comes from temperature. Global temperature before the satellite era is estimated from the surface network of thermometers, albeit with only partial coverage of the Earth. In blue is the induced component of CO2, again derived from the satellite MSU, but now determined only from temperature. As before, it tracks the observed record of CO2, in green. In black is the same information, but now based on the surface network from the Climate Research Unit. The sample inserted is shaded. Like the blue curve, the black curve represents the CO2 introduced by native emission through its dependence on temperature. It too tracks observed CO2 during the satellite era. In fact, it tracks it throughout the instrumental era, back to 1960, when atmospheric observations began. Observed CO2, that's the green curve, and the induced component, that's the black curve. Then both approach 300 ppm. Before 1960, the induced component continues to decrease, approaching 275 ppm in 1880. The uncertainty, which increases back, is then wide, ranging between 220 and 330 ppm. During this early period, continuous observations of atmospheric CO2 are non-existent. We have only proxy CO2. In green is the ice proxy you saw earlier. It too decreases backward, approaching 290 ppm in 1880. Let there be no ambiguity about what you're looking at. The black curve is just the integral of temperature, scaled by the observed sensitivity of CO2 emission. And the sensitivity of CO2 emission is derived only from year-to-year fluctuations in temperature. Short-term changes introduced by volcanic eruptions, El Nino, and other internal influences, which are independent of human emissions. The modest discrepancy before 1940, about 10 ppmv, lies well within the sampling uncertainty of the surface network. But in light of the agreement during the instrumental era, the last half century, it may actually reflect error in proxy CO2. It may also reflect limitations of the surface network. At the bottom is coverage of the Earth by surface thermometers, the CRU record. It maximizes near 1960 at 35%. That's how much of the Earth is land. Before 1960, coverage plummets. By 1880, coverage of the Earth by the surface network is less than 8%. The IPCC has proclaimed the following: all of the increases in CO2 since pre-industrial times are caused by human activity. The increased CO2 is known to be caused by human activity because the character of CO2 in the atmosphere, in particular the ratio of its heavy to light carbon atoms, has changed in a way that can be attributed to addition of fossil fuel carbon. The observed sensitivity of native emissions, through which CO2 increases with temperature and carbon-13 decreases with temperature, makes this impossible. And that brings us lastly to how all of this shakes out in the world of climate models. Plotted here is global mean temperature from CRU. The end of the 20th century is warmer than the beginning by just under a degree. But it's hardly a consequence of steady warming. Rather, it results from consecutive decades of warming being incompletely canceled by consecutive decades of cooling. The difference in global temperature results almost entirely from just two intervals. 2 decades during the Depression era, and 2 at the close of the century. Less than 30% of the record. And to be rhetorical, those are the only intervals when temperature has a trend of even the same sign as the trend of CO2. Removing those 4 decades out of 16 decades leaves a cooling trend. That's why the trend over the full record isn't even statistically significant. The 2 intervals of warming are equally long, yet during the first, CO2 was not much higher than during the 19th century. Since 1997, global temperature has experienced no warming. If anything, it's experienced gradual cooling. For nearly 2 decades, almost as long as the preceding warming. Global temperature is controlled by the global energy budget. The energy budget is measured in units of light bulbs. 1 light bulb is 100 watts. Shortwave energy from the sun, visible radiation, arriving at the top of the atmosphere, is some 300 watts per meter squared. That's equivalent to 3 light bulbs illuminating 1 square meter. Of that, 30% is reflected back to space by cloud, ice, and snow. The rest, the 70% not reflected back to space, is absorbed. Most of it passes directly through the atmosphere, which is transparent to shortwave radiation. It's then absorbed by the Earth's surface, which is thereby warmed. To maintain equilibrium, the Earth's surface emits long-wave radiation, infrared radiation, about 400 watts per meter squared, which acts to cool the Earth's surface. very little of it passes directly through the atmosphere, which is opaque to long-wave radiation. Instead, 95% of that long-wave radiation, some 400 watts per meter squared, is absorbed by the atmosphere, chiefly by water vapor and cloud. They are the primary greenhouse absorbers. 100% increase of CO2, methane, and all other greenhouse gases would add only 4 watts per meter squared, 1% of the absorption. To maintain equilibrium, the atmosphere also emits long-wave radiation. Almost as much is emitted back down. Representing the greenhouse effect, it too warms the Earth's surface, offsetting the energy lost through emission. In this picture, the atmosphere behaves as a blanket. The more atmospheric absorbers of long-wave radiation, the more layers of the blanket, and the greater this warming of the Earth's surface by downward long-wave radiation. The CO2 contributes to atmospheric absorption. Increasing CO2 adds layers to the blanket. However, most of the blanket comes from water vapor and cloud. Like everything else in this dynamic system, they change. Much of the long energy emitted upward by the Earth's surface, cooling, is offset by long-wave energy emitted back downward by the atmosphere, warming. To maintain equilibrium, the Earth's surface must therefore also transfer heat away mechanically. Through conduction and convection, vertical air motion, it carries heat away from the surface. Associated with cloud and rainfall, it accounts for 30% of overall heat transfer from the Earth's surface. 2 orders of magnitude greater than long-wave warming and increased CO2. Most of the mechanical heat transfer from the Earth's surface comes from the ocean. What can we say definitively about that contribution? 3 features make the ocean pivotal. First, observations of the ocean are limited, chiefly to the surface, which can be monitored by satellite. Buoys provide a recent record of the top 20% of the ocean. The rest, however, is virtually unobserved. The second feature pertains to our ability to interpret long-term changes, which requires averaging over many internal cycles of the system. Only then can we truly distinguish a long-term drift from an internal oscillation. The Earth atmosphere system is dynamic, changing on many timescales. Weather operates on a timescale of days. Seasons operate on a timescale of a year. The sun oscillates on a timescale of a decade. The ocean oscillates through its overturning circulation, the so-called abyssal circulation. It operates on a timescale of 1 to 2,000 years. Changes embedded in that internal oscillation will be manifest over centuries. Lastly, the ocean's large mass gives it a heat capacity, which is huge. Even minuscule heat transfer from the ocean can produce significant warming of the atmosphere. 1 degree of atmospheric warming would result from ocean cooling smaller than 0.0005 degrees. Even if we had observations of the deep ocean, measured in here, and observed variability are orders of magnitude greater. Global temperature is the most fundamental climate problem. It's the cornerstone of climate change. If anything is going to carry the signature of increasing CO2, it will. After all, climate models reproduced its previously observed warming during the 80s and 90s. That led many of us to speculate, well, maybe they are getting it. But reproducing the known change in global temperature is 20/20 hindsight. It's not a strong test of predictive skill. That experiment is called a hindcast. The real test is a forecast, predicting future evolution. Only then can one be confident that models have been tuned to match observed behavior. That's tantamount to a double-blind test, the standard of rigor required in clinical trials of pharmaceuticals. Neither the patient, nor the model, nor the clinician, the guy running the model, then knows the outcome. In blue is the forecast evolution of global temperature, averaged over 24 models of the IPCC, representing the consensus. The mean evolution is free of decadal variability, which must therefore be incoherent between the models. Remember the plot of spaghetti, whose mean was the climate model consensus? Their incoherence implies that on decadal timescales, the models have no predictive skill. Notice, this is the same timescale responsible for almost all of the 20th century warming. 2 decades during the Depression era, and 2 at the close of the century. The only feature common to the models, retained in their mean, is a centennial drift. It increases monotonically, becoming 3.5 degrees warmer by the end of the 21st century. The increase in global temperature should correspond to increasing CO2. In fact, the correspondence is considerably greater. In green is the forecast evolution of CO2. It too increases, exceeding 800 ppmv by the end of the century. Global temperature doesn't just increase with increasing CO2. It tracks it almost perfectly. In the modeling, the part consistent between all of those models, changes in global temperature and CO2 are isomorphic. They have exactly the same form. Their relationship is so tight, you don't even need a climate model. A fractional increase of CO2 entirely determines the fractional increase of global temperature. The simulated relationship is remarkable. Here's why. Remember the global energy budget? It is what determines global temperature. Increased CO2 contributes to the energy budget, but only at the 1% level. The 1-to-1 correspondence indicates that changes of global temperature remain in equilibrium with changes of CO2, but nothing else. Dominant contributions to the energy budget either do not change, or if they do, they are enslaved to CO2. Those contributions can change only in direct proportion to CO2, which in the model controls everything. Reflected shortwave energy, which depends on cloud and ice, can't change independently. Mechanical heat transfer near a surface, which depends on the ocean circulation, can't change independently. And 99% of the long-wave energy soared by the atmosphere and re-emitted back down, which depends on water vapor and cloud, can't change independently. In the model, changes in the global energy budget are reduced to a highly simplified balance, driven exclusively by increased CO2. This means that 1% of the global energy budget wags the other 99%. In blue is the observed record global temperature from the 7 MSU. In green, the observed record of CO2. The long-term evolution of global temperature parallels that of CO2 during the 1980s. It's been scaled to match the trend as was obtained by models at the IPCC. That's what you saw in the spaghetti part at the start. With the count of the eruption of Pinatubo in 1992, their correspondence is similar during the 1990s. After the El Nino of 1997, CO2 continued to increase. Global temperature did not. Their divergence over the last decade and a half is now unequivocal. In the model, global temperature tracks CO2 almost perfectly. In the real world, clearly doesn't. Model world, real world. This leads to the following conclusion. In the model world, changes of CO2 and global temperature are closely related. In fact, within a scale factor, the two are synonymous. In the real world, they're not related. Not quite. The correct conclusion is they're not related directly, as they are under the simplified energy balance that prevails in the model. Recall, on short time scales, changes of CO2 are controlled by native emissions. Remember the correlation between net CO2 emissions and temperature? CO2 then evolves, not like temperature, as it does in the model, but like the integral of temperature, the sum of temperatures. In dotted blue is the integral of observed temperature. It tracks observed CO2, even after the 1990s, when the observed records of CO2 and temperature clearly diverged. If CO2 tracks the integral of temperature, which it clearly does, it cannot track temperature, which it clearly doesn't. In the model, CO2 and global temperature are related directly. In the real world, they're also related, but differently. The distinctly different relationship between CO2 and global temperature represents a fundamental difference in the global energy balance between its evolution in the model world and the real world. If the global energy balance is wrong, everything else is immaterial. If we can't predict global mean temperature, we can hardly predict regional conditions, let alone extreme but infrequent regional conditions. The different relationships between CO2 and global temperature becomes manifest after the 1990s, when their observed records diverged. But once the temperature dependence of CO2 emissions is accounted for, namely by native sources, the two observed records are entirely consistent. These features of the observed evolution have the following two-pronged implications. In the real world, global temperature is not controlled exclusively by CO2, not even on long time scales, as it is in the model. In significant part, however, CO2 is controlled by global temperature, as it is approximate. I'll close on a general note, and you'll want to pay attention, because afterward there will be a test. At stake here is more than climate change, more even than the massive public funds that have been diverted to this cause célèbre. Take a good look around. The lights, the projection and audio system, the supporting electronics, even the chair that suspends you above the floor, rely on technological advances that all rest on the shoulders of science. Science is the foundation of modern civilization. It's important, therefore, to understand what is science, and equally important, what is not. Science is a balancing act. We theorize how things work, and then test the concept against observed behavior. In isolation, neither is science. You can develop countless models and run them to compute one mindless scenario after another. You can compare the models, even average them to form their consensus. If they're not tested against observed behavior, that process becomes a self-perpetuating industry. You can collect countless data, catalog them, compare them with statistics, even form their consensus. But if not tested against physical principles, rigorously, and from all angles, that process becomes a self-perpetuating industry. Each of these perspectives serves as a safeguard on the other. It is the ongoing challenge between them that eventually leads to the truth. That is science. Discourse is thus essential to science. Without it, all that remains is propaganda. Silencing discourse through intimidation, or worse, is to put a Luger to the head of science, and with it, what makes our civilization modern. There is no morality in scientific findings. There is only objectivity. Nor is popularity relevant. Politics turns on plurality. Science doesn't. In science, consensus is meaningless. This principle is expressed clearly by one who is in a good position to know. Einstein's theory of relativity had some peculiar implications. Among them was that somehow light could be bent by gravity. There arose numerous experiments to prove this theory. Upon reflecting on them, Einstein remarked, "No amount of experimentation can prove me right. A single experiment can prove me wrong." That was, in effect, what Einstein did to Newton. In science, only one vote counts: Mother Nature. The climate model consensus you saw earlier, the driver of government policy, fell victim to the illusion of plurality. The models all locked into the observed warming during the 80s and 90s, which was then extrapolated forward on the basis of CO2. They overlooked a small matter. Mother Nature was on a different track. Oh, she passed through the same station in the 80s and 90s, but hers was on a different track. Had we not the benefit of subsequent observations, had we been blinded by intimidation, we would never have known. Einstein's remark underscores the continuous testing, the question behind critical thinking that is inherent to science. It is the repeated tempering of the metal from which it draws strength. It was in fact through such questioning and new perspectives it opened, through which Einstein revolutionized science. And so, if you find yourself being lectured by a purported expert on the science which he proclaims is separate, you can be confident you are being counseled by an impostor. Folks, the purveyors of the message desperately want you to believe them, and with equal desperation, to hear from no one else. Me, I couldn't care less. I don't want you to believe anything. I want you to think. And if you're not thinking, what are you doing?
Appreciation of Murray's presentation. And as we said, there's an opportunity for coming back for questions, yes? Or do you want...
I have one more thing to do.
One more thing to do.
In keeping with the scientific method, I promised you a test. Relax. There's only one question. A good test should be a learning experience. No one should leave this talk without a tangible grasp of its implications. We considered many sources of CO2, but one was not made explicit. You. Humans absorb oxygen and expel CO2, like all members of the animal kingdom. We thus enrich CO2 in our environment. Now, also in this complex is the House of Lords, where Parliament sits. And from what I've seen, that's the site of a lot of CO2. Fortunately, the parliamentary chamber is cavernous. It contains a large volume of air in which CO2 is dissolved, limiting its concentration. The chamber, for our purposes, will have a volume of 1,000 cubic meters, typical of a large house. Now we need a subject. The logical choice is a lord or an MP. But that might be unrepresented. No, we need someone with unflinching resolve and composure. One who's not intimidated by circumstances. If you know what I mean. Here's the perfect subject. Her Majesty has graciously consented to participate. The parliamentary chamber is cleared, after which she's escorted in. The doors are locked and the windows sealed. Like her subjects, Her Majesty produces CO2, which must therefore increase in concentration in that large chamber. All right, here comes the question. How many breaths per day can Elizabeth take without increasing CO2 in that large chamber faster than it's increasing outside in nature? And in the spirit of cooperation, if not naivete, Her Majesty has graciously consented to hold her breath until you provide the correct answer. By my estimation, you've got about 60 seconds. Okay. What's your gut feel? Well, that's a safe one. Whatever you do, don't cop out with God Save the Queen. Come on, take a guess. I won't tell. Yes, sir. Take a guess. It's a good guess. But no cigar. Someone else. Wrong direction. But a good guess. Someone else. I'm giving you a hint. Well, she's counting on you. 5. It's too low. She's getting desperate. 50. For CO2 in that large chamber not to increase faster than it is outside in nature, Her Majesty can take no more than 50 breaths per year. Think about that when you're next in the financial district, watching the frenetic pace of business people scurrying to their next appointment. Oh, yeah. All right. Thank you.